This is a problem from winter 2022, problem 4. And the problem asks us to sketch the graph of a function g of x satisfying all of these following conditions on the axis provided below. So obviously that's many conditions. Let's just go down the list one by one. The first condition says that the domain of g of x includes the open interval from -6 to 9. And we see that in this provided grid below, we in fact have enough space for anything from -6 to 9. We just gotta make sure we use all of it. So since the domain is anything from -6 to 9, something like this is not going to be allowed. So maybe a function like here, the domain is not including numbers in this range. For example, -1 is not in the domain of this function. So this would not be a correct answer. So we just want to make sure that the function is defined throughout this grid. And the second condition is that from -6 to 0, the function g of x, which we want to sketch below, is the derivative of the function m of x, which is shown in this graph to the right. And here they give us some clarification about m of x, that it's a linear function between -6 and -5. So we see that in this curve that from -6 to -5, so in this region, we know it's just a line. And we also know that this curve is constant between -1 and 0. So we know from -1 to 0 in this range, we know the function is not changing. It looks like something like -1.5. So let's actually try using the information below. So we know from -6 to -5, m of x is just a line. So we know that g of x, which is the slope of m of x, is going to be constant. And whatever g of x is going to be is really going to be the slope of this line segment here. And what is the slope of this line segment? Well, the change in x is 1. Change in y is 2 here, looking at the grid. So we know the slope of this portion from -6 to -5 is always 2. So that's telling us that g of x is going to be 2 from -6 to -5. So we know this information. Not only that, we know m of x, in fact, is constant from -1 to 0. So here the slope in this part, the slope is always 0, which is telling us that our g of x is going to be 0 between -1 and 0 right here. Moving on, let's see what other conditions we need to use. To start with, realize that we actually have a 0 of the derivative. So if I look at this particular point in -4, we see that the tangent line is horizontal. So we know that at this particular point, the slope is 0. So that's telling us that at -4 and -4, we want to have a slope of 0. And what else do we know? Well, looking at this graph, we're increasing from -6 to -4. So we know the derivative of m of x, so g of x. So we know g of x is positive in this interval. So we know g of x here, since m of x is increasing, is positive. And we know in this interval, because m of x is decreasing, we know g of x is going to be negative. But there is more you can say. Because if I look at this curve from -6 to, say, like around somewhere here, we see that the curve is actually concave down. So I'm saying like in this region of the curve, we are concave down. One way of seeing this, what I like to do is like if I try drawing two eyes here, this portion of the curve actually looks like a frowny face. Like when I draw two eyes, we see that we are making a frowny face here. Whereas if I look at this portion of the curve, we see that when I draw two eyes, we are making a smiley face. So this part is actually concave up. So this part is concave up. Obviously, the smiling face and frowny face is not really what you want to write down for the exam. I guess another way of seeing concave down and concave up is that when I draw a tangent line, so when I try drawing a tangent line to this curve at any portion in here, we see that the graph of the curve is lying below. It's lying below the tangent line. Whereas when I try drawing a tangent line to the part of the graph where it's concave up, we see that the graph is in fact lying above the tangent line. So this is another way you can distinguish. And this is essentially really saying that for the part where it's concave up, the graph is opening upwards, and the part where it's concave down, graph is really opening downwards. So this is the kind of thing that's happening here. And what does concave down and concave up tell you? Well, let's just try looking at the slope of the tangent line. So when I look at the slope of the tangent line on the portion where it's concave down, we see that the slope is decreasing. in the sense that here maybe slope is 5, here maybe the slope is decreases to 2. I mean, I don't think these are exact numbers, but obviously the slope is going down is really my point. At this point, slope is 0, and here maybe the slope is like -3, and here maybe the slope is like -5. But my point is that the slope goes from very positive to less positive to 0 to a bit negative to very negative. So when the graph is concave down, the slope is decreasing. Another way of saying that is that the derivative of m of x or j of x is actually decreasing on this range. So we can conclude that j of x is decreasing from here to here. And I guess maybe this wasn't super clear that j of x greater than 0, this applies to where m of x is increasing. So from here to here is where j of x is positive. Anyway, just to continue this discussion, we know where it's concave up. If you look at the slope of the tangent line, you'll see that the slope of the tangent line, which is really given by j of x, is increasing. And that's because when I try drawing the tangent line, it goes from very negative slope to less negative slope to even less negative slope. So the slope is actually increasing here from, say, this point to around this point where the graph just becomes a horizontal line. So I think that's more than enough information for us to give a sketch of the graph. So we know, once again, from -6 to -4, j of x should stay positive. So we know we should stay positive in this region. And not only that, we know from -6 to around this point, which is like -2.5, j of x is decreasing. So we know up till around -2.5, j of x should continue to go down. I guess it might be worth pausing here and thinking about how much farther is j of x actually going to go down? What's going to be the minimum it's going to take? Well, I mean, how far it's going to go down is going to be the most negative slope we are going to have on this graph. Well, it looks like the most negative slope is happening around this -2.5. And if I try sketching a tangent line here, so maybe I can do it in a slightly different color. So if I try sketching a tangent line, I think it looks something like this. Just from looking at it, I'm not super sure what the slope of this line is, but I guess it looks like about change of x is about 1 and change of y is about maybe about -3. So I think you can just guess and check. I highly doubt that getting the most negative slope exactly right, it matters that much for the points. I'd be very surprised if you lose any points, in fact, if you just eyeball it. So I guess like we know at -2.5 it's gonna go down to somewhere around -3. So let me resketch that part of the graph. So the graph is going down, something like this. And from -2.5 to around -1, remember that the graph was concave up. Just going back up, the graph was concave up here, which means that j of x, the derivative, is increasing. So we want to see something like this. And I think it actually makes sense to keep this part of the curve about symmetric with respect to each other. And the reason for the symmetry is if I go back up, the part of the curve from -4 to -1 it actually has some symmetry, in the sense that when I move a little bit from the central point and I sketch the tangent line, and I move a little bit from the central point and I sketch the tangent line, it does look like the slope of these two lines are the same. So it does look like you have some nice symmetry about the center point for the slope from the graph. So I think it's reasonable to make it symmetric for j of x. Anyway, I think that's all the information we need between -6 and 0. The rest of the conditions, if we look at it, are really for x greater than 0. So let's go down and incorporate them into our graph as well. The first thing they're telling us is that it should be continuous between 0 and 5. So we know between 0 and 5 here, we cannot do something strange like having a jump. Something like this is not allowed. Having a hole, something like this, is not allowed either. You should be continuous between 0 and 5. And what do we also know? We know the graph is increasing and concave down from 0 to 3. So we know from 0 to 3, we know the graph has to be increasing and concave down. Well, increasing and concave down looks something like this. So something like this. So it makes a frowny face. So it's concave down and it's clearly increasing. I'm not sure if I'm violating any condition here. Let's go up and see. Well, they tell us that the average rate of change from 3 to 5 also should be -1/2. So let me actually make this graph a little nicer. why don't we actually go up to something like maybe some integer point, so like 3. And the reason I'm doing this is because you know the average rate of change from 3 to 5 is some specific number. So if I make this point stop at some integer value, this condition is going to be easier to enforce in the sense that you want the slope of the line to be negative 1/2. So that's change in y over change in x. And here you're going from 3 to 5. So that's change in x of 2. So you know we should have a change in y of 1 from 3 to 5. So since I picked 3 as the y value for 3, so at 5 I think all we need is a point here. And it looks like there are many possible answers, obviously, that incorporate these two conditions, right? For example, I could have gone up to 6, and I could have gone 1 down. Maybe now f of 5 is j of 5 is 5. This would be a perfectly valid solution, I believe. All we are given between 3 and 5 is just the average rate of change. We don't know anything else. So these 2 points, I guess, is kind of forced by the fact that we picked this point. But anything in between, anything that's happening in between 3 and 5, anything's okay as long as we make it continuous. So even something like this would be okay. So I just drew some continuous graph connecting these 2 points. You can do anything reasonable. And then we see that the limit as x approaches 6 of j of x does not exist. So we want to make sure that at 6 some problem happens, but there's actually one more condition, that j of 6 should also be negative 3. So let me actually combine this information. So you know at 6 you want to output negative 3, so you know you have a point here, and we just want to make sure that it's not continuous. It's not continuous at 6, and I mean there are many ways of doing this. Maybe I can put some sort of jump where your curve is going down, but at 6 you're jumping all the way down to negative 3. So that takes care of this condition. And to take care of this condition, all we have to do is perhaps like continue this point on for a little more like this, because this ensures that the left-handed limit and the right-handed limit are different. From the left, you're approaching, say, 1 here. From the right, it looks like you're approaching y value of negative 3. So the limit at 6 does not exist. So this condition is satisfied. And now finally, we want to make sure that the instantaneous rate of change of j of x at x equals to 8 is 2. So we just want to make sure that the slope of the graph of j of x is 2 at 8. So I guess like one easy way of enforcing that is to just make it linear. So maybe make it linear with slope 2. So here I'm just making it have slope 2. Change in x is 1, change in y is 2. So I just made the graph linear in this portion with slope 2. And I guess all we have to do is make sure that the graph is well defined elsewhere. So I guess I can erase this a little bit, and I can just connect it. I can connect it from the start all the way up to here.